So what we saw was we had C as R transpose 1 by sigma 1, C inverse as R transpose 1 by sigma 1 squared, 1 by sigma 2 squared, so on up to 1 by sigma n squared R, right? Now what we did was we assumed, we saw that this was very close to eigenvalue decomposition. Fine. Now so we started saying C inverse as some R transpose and this as some D inverse and then this as R. Fine. Then we wanted to invert this. C inverse is R transpose dr, but before that, so as to keep in track with EVD, which had A is equal to V D V inverse, which had this, we will make R transpose is equal to P. Therefore C inverse will become P, okay, there was a D inverse P transpose. Fine. Now if I make C here, from this, that will become P D inverse P D P transpose. Do you get that?
Yes.
And then this was the form we had for our covariance matrix. Now I have this C D P C P D P inverse. Okay. Now I want to find C transpose, right, which is P D P transpose whole transpose. That will actually be P D transpose P transpose. Why? Because its transpose will come here, its transpose will come here, its transpose will come here. Now what do you observe from here? This is equivalent to C from here. So we have C transpose is C. Okay. This is the first property of covariance matrices. Fine. This was the first property of covariance. So we can say, we say that covariance matrices are symmetric. Fine. Now C is equal to P squared. Fine. Now what were these? Variances in the variances sigma I squared are variances of the variables, random variables xi's, aren't they? Sigma I squareds are variances of random variables xi's. Now once you have obtained this and once you have multiplied this, now in these okay, xi dash, random variables xi dash. Now what were covariances of xi dashes? They were all 0. That means the covariance of xi comma xj for I is not equivalent to j was 0. From this, because there is a huge portion of 0 here. How did we get this? Because we observed that in the two-dimensional case, this was how it looked. And we defined covariance as something which was x1, x2 for each times sigma from I is equal to 1 to number of samples. isn't that? And that was 0 for this case, and it was positive for this case. So let us see this. Covariance is 0 for this case. What is covariance for this case? It is positive.
Yeah, positive.
Because it is in the second and first and third quadrants. Most of the points lie in the first and third quadrants where the product of the two coordinates is positive. So covariance is positive here. And then when do we have a negative covariance? The other way around.
When it lie in the
Yeah.
second and
When most of the points lie in the second and fourth quadrants. So this will be a case of negative a case of negative covariance. Negative because the second it is in the second and fourth quadrants. Second and fourth quadrants where the product of coordinates is negative. Fine. So now what do you see here? These covariance, what do they imply? They imply that these data, they somehow have a linear relationship, isn't it? Doesn't that show that x1 and x2 has a linear relationship? Similarly, here you have positive covariance which implies a positive slope. You have negative covariance which implies a negative slope. Okay, so let us see that. Positive covariance implies a positive slope of the linear relationship. Similarly for negative. Okay, and if they were uncorrelated, the slope was almost 0. Okay, or sometimes it could also be infinity if this was the major axis. But here it is 0. We can always rotate it the way we want. So these zeros have come from these things, isn't it? These zeros have come from these, and these zeros have come, and these diagonal values have come from these things. Do you see that? So we are putting these values here. And we are seeing if there is a slope. If there is a slope, then we are correspondingly putting these zeros. This is just a motivation behind how covariance matrices were defined. Okay, so that comes to from there we come to the actual definition of covariance matrices. So we will define for zero mean. Zero mean random variables first. and then generalize to general cases of non-zero mean random variables. Okay, so
Yeah.
what is that definition? It is given as, the covariance matrix is given as E of x1 x1 squared one second, we'll just save it. So that is given as the expectation of x1 squared, expectation of x2 squared, so on up to expectation of xn squared in the diagonals. For zero mean, these are the variances. For zero mean, E of x1 squared, E of x2 squared, so on up to E of xn squared are the variances, which were equivalent of sigma 1 square, sigma 2 square and all. And these were actually zero in what we were seeing, because it was the frame where these ellipses were along the major and minor axis. The frame that we were looking at, x1 dash, x2 dash and xn dash, there the covariances were zero. That means the ellipses were were along these major axes, x axis and y axis. The major and minor axis of the ellipses were along x and y axis of your original frame. But here that may not be the case. So these things here are non-zero. So what are these non-zero things? E of x2 x1, E of x3 x1, that is expectation of x3 x1, similarly expectation of xn x1, right? And then you have here expectation of x1 x2, so on up to expectation of x1 xn, and so does this table complete. Now what are these expectation of xi xj for I not equivalent to j, for zero mean, of course.
These are the covariances.
These are the covariances. So is the covariance of zero mean random variables xi and xj. Okay, this was one way how. So this was one way how covariance matrices were motivated. Fine. So let us have a look at this. What is it? E of x1 squared, E of x2 squared, so on up to E of xn squared. This is E of x2 x1, E of x3 x1, so on E of xn x1 expectation. Expectation of x1 x2, expectation of x1 x3, expectation of x1 xn. This is your matrix. Now I would want to, since expectation is a linear operator, I would want to bring expectation outside and write these inside. So that will be expectation of x1 squared, x2 squared and so on up to xn squared. x1 x2 will be here, x2 x1 will be here, x3 x1 will be here, xn x1 will be here, x1 x2, x1 xn and so on. Right? Now how can you see this? This can be seen as expectation of, see, what is the rank of this matrix? Can you just see and tell?
Right.
It's actually a rank 1 matrix. If I can write it as, can I write it as this? Okay, I'll write it in a new page. Can I write this matrix as? Yeah. X2, X. Yeah. Exactly. Yeah. So you can always write this as xn. It is a tensor product of. This is called a tensor product or an outer product. Two column vectors. Since we are able to write it this way, its rank is 1. Okay, since there is no new information other than just this vector, you don't have any new information other than just this vector. Just this vector has been scaled several times and has been placed in this matrix. Do you see that? The first one is.
The first one is scaled by x1.
The first one is scaled by x1. The second one is scaled by x2. Okay, so let us make that clear here. X1 times x1 x2 to xn. Second one is x2 times x1 x2 xn, and so on up to xn times x1 x2. So the number of independent columns is only this. Only one independent column. Independent column. Okay, so covariance matrices are rank 1 matrices. Okay, now, but they are rank 1 matrices, but they are still, what do we have them as? Not covariance matrices, these matrices. Okay, these matrices are rank 1 matrices. Because covariance matrix is the expectation of this x1, x2, so on up to xn, and then x1, x2, xn. Not covariance matrices. These matrices. These matrices are rank 1 matrices, but these are not rank 1 matrices. Had these been rank 1 matrices, we would not have been discussing all this, because we need to invert this. So this is your covariance matrix. So this matrix, now assuming that this is a vector, x is equal to x1, x2, so on up to xn. We have C as expectation of x transpose. Oh, did I write it wait. I wrote it the wrong way here. It is this. x1, the tensor product is this. Similarly, I have the tensor product here as that. Right. So we define for 0 mean random variables, we have C is equal to expectation of x transpose, where x belongs to Rn. Fine. Now this now let us take a new approach. Towards the same. Let me say we have random variables x1, x2, so on up to xn. Okay. Now let us consider a linear combination of these random variables. What would that combination look like?
Sum
Alpha 1 x1 plus alpha 2 x2 plus so on up to alpha n xn. Say I form a new random variable y with this. Here we have random variables x1, x2, x3. So this xi will belong to R, just R, and here these alphas will also belong to R. Fine. Now y is given as alpha 1 x1 plus alpha 2 x2 plus so on up to alpha n xn. Right. Now we can write this as y is equal to alpha 1, alpha 2, so on up to alpha n as a dot product of two random vectors which may not be of any physical importance here. Making these as a random vector may not be of a physical importance here. Just for some convenience. So I'll write this as alpha transpose x, where alpha is given as alpha 1, alpha 2, so on up to alpha n, and x is given as x1, x2, so on up to xn. Okay, so we now have this simple y is equal to alpha transpose x. Now let me say I want to find the variance of y. What will the variance of y be? It will be e of y minus e of y the whole squared. This is the variance of a random variable. Now let me say here x's were not zero mean random variable. The mean of each xi is mu I. Okay, so now I want to find the e of y. That will be e of alpha 1 x1 plus alpha 2 x2 plus so on up to alpha n xn. This will be alpha 1 e of x1 because e is a linear operator, alpha 2 e of x2 plus so on up to alpha n e of xn. This will be alpha 1 mu 1 plus alpha 2 mu 2 plus so on up to alpha n mu n. Okay. Now we want to find e of y minus alpha 1 mu 1 plus alpha 2 mu 2 plus so on up to alpha n mu n and its whole squared. Isn't it? This is variance of y. Now observe that we would again want to make a notation here, which is the vector mu is mu 1, mu 2, so on up to mu n. Okay, so this alpha 1 mu 1 plus alpha 2 mu 2 plus so on up to alpha n mu n will reduce to alpha transpose mu. Notation. Fine. So what do we have here? Variance of y is e of y minus alpha transpose mu whole squared. Fine. Now y minus alpha transpose mu belongs to R.
Yes.
Now y minus alpha transpose mu, transpose will also belong to R and is equivalent to y minus alpha transpose mu, because it's a scalar. So I want to write alpha minus y minus alpha transpose mu whole square as y minus alpha transpose mu times y minus alpha transpose mu transpose. Okay, I want to write it this way. Now what do I do next? So variance of y will be given as E of y minus alpha transpose mu times y minus alpha transpose mu, right? Now we have y as alpha transpose x that we defined here over here using this. Later point. Okay, so using that here it will become E of alpha transpose x minus alpha transpose mu into the same here alpha transpose x minus, okay, there was a transpose here, alpha transpose mu transpose. Okay, now you will write this as variance of y is what? This alpha transpose will come out, alpha transpose x minus mu, and here it will be the same thing, alpha transpose x minus mu the whole transpose, right? Because its transpose was here. This will become E of alpha transpose x minus mu times x minus mu the whole transpose alpha, because it's now alpha transpose and alpha are constants, so I can get them out. Alpha transpose E of x minus mu into x minus mu transpose alpha. Okay, now let us say x minus mu is equal to x tilde, and x tilde is a zero mean random variable. So this will become alpha transpose E x tilde transpose alpha. This is the exact derivation of the covariance matrix. Exactly how someone motivated to define Cx. Okay, so we'll have Cx as E x minus mu times x minus mu transpose. Okay, so this is the definition of covariance matrix. Definition of covariance matrix for any real random vector x belonging to Rn with mu as the mean vector of x, we define the covariance matrix C as E x minus mu, expectation of E x minus mu transpose. That's it. Okay, so what is the conclusion? We conclude that from all this, we are only making Gaussian assumptions. In all our calculations, isn't it? Because we assumed a Gaussian distribution and derived all this. This has to be kept in mind, or a normal distribution. To derive this is not true for any distribution. It is true only for a Gaussian distribution. That means covariances, these all are actually defined for those variables that are Gaussian distributed. Okay, this is fine. Now, so we can have these Gaussian contours any way we want. So let us see this. P of x is given as 1 by square root of 2 pi sigma 1, sigma 2, so on up to sigma n, e to the power minus half times x transpose. There was a p transpose, there was a d, and then there was a p, then x, right? Then we said p transpose, okay, there was a d inverse. D inverse p is cx inverse, right? Now substituting this, px is 1 by square root of 2 pi, okay, power n. Okay, there was a power n. Didn't I write it earlier? Yeah, I would have written. So there is a power n. This is sigma 1, sigma 2, so on up to sigma n. This is e to the power minus half x transpose cx inverse x. Okay. Now let us see what this is. So what do we have now? We have sigma 1, sigma 2, so on up to sigma n in the denominator. Now let us see what this is. Now we have this as the square root of sigma 1 squared, sigma 2 squared, so on up to sigma n squared. Now once this is done, let us see what this sigma 1 squared, sigma 2 squared, so on up to sigma n squared is. This is product of diagonal elements of the matrix D. Determinant of a matrix is product of eigenvalues. Isn't it? Once this is done, what can we say about what more can we say about this? Determinant, we already know that determinant of a matrix is the same as the product of its eigenvalues. Now determinant of Cx will be what? It will be sigma 1 squared, sigma 2 squared, and so on up to sigma n squared, where sigma 1 squared, sigma 2 squared, and sigma n squared are the eigenvalues of C. Now once this is done, we have p of x as 1 by square root of 2 pi power n, square root of determinant of Cx, it is a power minus. This is our complete multivariate distribution. So this is our complete multivariate Gaussian.